Hi, everyone. This is Rob Gray from the ASU and the Perception Action Podcast, back with another article review. In today's episode, I want to review this really interesting new article looking at how variability of a practice, so they're going to use the classic random blocked comparison, influences how we search solution space and task space. And I'll get into what those mean again. So the specific paper I'm talking about here is this one by Raoul Bongers and colleagues at University of Groningen. Does lots of great work on motor learning, skill acquisition. This is the paper in General Motor Learning and Development. Okay, so what they're talking about here is when you have a task that has redundant solutions. So multiple degrees of freedom, right? There's multiple different ways we can produce the task, multiple combination of joint angles, joint movements. Um, the way that they can produce, we can use it. You can search both within the task space, which is basically coming up with a new information movement control law, and within the effector space, within the joint space, right? Different ways to produce that law, right? Different combinations of joint movements to achieve that law. So those are the two different ones. So the idea is that they want to understand how new learners learn, search this space, and how it's influenced by the variability design of practices, right? So we get the search process, searching in the task space, which is going to be the end effector, and searching within the joint space, right? Sometimes I refer to these as essential and elemental variability. Okay. So in this study, what they're going to do is, that's kind of the basic background. In this study, they're going to you're searching for coordination patterns in two different spaces. So they want to understand how that occurs. Right? They're going to impose variability in the schedule of practice and using random versus block practice. And they're going to look at search in a few different ways. One of the main ways they're going to use is our old friend, the uncontrolled manifold analysis, looking at the variability partitioned along the manifold and orthogonal to the manifold. You know, the classic good versus bad variability, which will affect how you perform the task. Okay, so that's the basic thing. What they're hypothesizing is that the random group will do better in the transfer task after practice, the classic random versus blocked effect, largely because there'll be increased evidence of search during acquisition, both within the joint space and within the task space. Okay, so that's what they're going to test. The basic task they used was a simulated interception task. So basically, you had your arm free to move. It has motion trackers on it, IMU units. Your movement of your arm controlled. You basically were holding, essentially holding a mouse. The movement of your arm controlled the movement of a paddle on the screen, and you had to slide the paddle to enter. So they're playing Pong, basically video game Pong. I've used this as a task, as a very good task for understanding motor control. So you're moving your elbow and wrist during the movement. So they have multiple degrees of freedom. They're trying to intercept the approaching ball, shown in green, which is going to have varying different trajectories, right? So the ball is going to start in different positions, go in different angles, so it has different trajectories, and things like that. When you intercept the ball, the paddle is going to turn a different color to give you feedback. So that's the basic design. There's 4 sessions. There's a pre-test, practice, post-test, and a transfer test. In the pre and post and transfer tests, you're going to do 16 trials. Each of the different ball trajectories presented once, right? And what we're going to do is, practice. We're going to in the pre and the transfer test is obviously going to be the test that you didn't train in. The classic way we do block versus random. So the people that are playing in block, they're going to have to try to do it random, where trajectories vary randomly, and people that train in random variation and trajectory are going to test in blocked, right? And they're going to both. So it's a classic design of mini variability of practice studies. Okay. In the practice, they're going to do 512 trials, which represents 4 phase of 128 trials. They're varying either the blocking, the start position, right? So they're always starting at the same position. They use different to do different angles. They're doing in the random group, they're doing pseudo randomizing the starting position to give you various trajectories, right? So variability is occurring at the level of the practice conditions. Okay, with 8 repetitions of each trajectory. Okay, so again, there's nothing kind of the novel thing is in the analysis, right? This is kind of the standard block versus random condition. Okay, so the first thing they looked at was task performance, and overall, you're going to see later that there's kind of mixed evidence of a benefit of random versus blocked in this study. In some ways, they got the typical pattern of results, as shown here in this figure, showing absolute error at the end of training. At the end of training, the block condition has lower error than the random condition, right? You're better at the end of the acquisition. When you switch to the block test, both groups do equally well, right? When you measure them in the block condition. But here's the big difference, right? When you measure people in the random condition, the people that trained in the random condition, which is, of course, what occurs in a real situation in game or competition, right? You get random trajectories. They perform bad. The random group performs better than the block condition. So, as I say, random the benefits of random practice typically show up in retention and transfer conditions, not during the actual training, right? It might actually make you slightly worse during skill acquisition, right? So in some ways, they got the standard effect. They got this was a significant interaction. In other ways, they didn't produce because we didn't get the overall result. But it's somewhat supportive of this. But that's not the main point, right? That's just the kind of the overall task. What they're looking at more is search, right? So the way that they're going to quantify search is kind of a similar way we've talked about a lot on the podcast, where you look at successive trials, right? And we look at how similar your movements are on trial n and n-1 and n-2, right? For the same trajectory, right? They're looking at the distances between the sum of the distance between the paddle spaces in 3 dimensions. They're looking at how much you're varying, right? How much you're varying for the same trajectory. And they can get a measure called path length, which is essentially a measure of how much it varies over these times. Okay. And they can measure both in task space, right? How much the end effector changed, and joint space, how much change in shoulder, elbow, and wrist angles you was used to produce that particular solution, right? At the task level, right? So people use more different positions of movements of the actual hand itself. So you think about it. If we just looked at how your hand moved to catch the ball, right? If we looked at how fast it moved, how quickly it accelerated, which direction, those things. We're just looking at your end effect, your hand, right? What you see is more evidence of variability. So they're moving at different speeds, different accelerations, different angles, right? So there's more search in the random practice, and here's this path length variable showing there's greater separation difference between your movements on trial n versus trial n-1. So you're exploring different end effector ways to get to the ball, right? To intercept that ball, different velocities, different accelerations, right? So essentially, you're exploring different information movement control laws, right? What's the best way to get your hand to that? And you can see over all the practice sessions, the path length was significantly higher in the random condition, means people were exploring different ways to get that end effector to the tip. Okay, so the hypothesis was supported in the task space, right? How about the solution space or the joint space, right? So here we're talking about for the same movement, right? So if I'm moving my hand with the same speed, so I'm using the same information control law, I can do that in multiple different ways. I could do it with all shoulder joint, combination of shoulder elbow, combination shoulder elbow wrist, and multiple. I have a system with redundant degrees of freedom. Again, how much did people explore different solutions for producing the same information movement control law at the task level? And again, what they found was people on the random condition had significantly higher in this path length measure. At the joint level, was significantly higher for the random condition than the block condition. There's also evidence that in both these I didn't mention, the variation is going down with practice, right? So your evidence kind of newels exploration to exploitation, right? So you're searching a lot at first, and over time it's reducing. But again, you're searching more in the random condition. So variability to practice is encouraging more search. Right? That's what we want to see. Okay, finally, the UCM analysis. Remember, so the UCM analysis, uncontrolled manifold analysis, partitions the variability in a movement into variability along UCM, along the manifold, which we commonly call good variability, because variability, that's shoulder, elbow, and joint movements that will all get your hand to the same place, right? So that allows for repetition without repetition, getting your hand to the same place with different combination of joint configurations, right? That's variability along the manifold. It's called good variability because it allows you to adapt, right? You can adapt to different conditions. You could adapt if your shoulder got fatigued. You can adapt to, different. So it allows for adaptability. It allows for repetition without repetition. The other type of variability, variable orthogonal variability, is variability combinations of the elemental variables, the joint, the variables like elbow, shoulder, and wrist that take you out of your solution space, take you off the manifold, right? So the combinations that are going to lead your hand to be there too early or overreach, right? So they're called it's typically called bad variability because, right, it's combinations of solutions. It's variability that's going to lead you to be unsuccessful in intercepting that ball, right? Which you don't want, of course, right? So what we do in this is we partition the two into, and what you expect, the basic hypothesis we expect is that in ecological dynamics, right, with experience, we get some evidence of reducing the overall variability, but more importantly, we get evidence of restructuring the variability. We get more good ratio of good to bad variability, which is also called the index of synergy, goes up. And what they found was, here's a plot for the random group. What you can see is initially they have a relatively the amount of good and bad variability is about the same. Over time, the ratio is increasing, right? The good bad variability is falling at a faster rate than the good variability. So we're increasing. Yes, overall variability is going down, but also the index of synergy, the ratio of good to bad variability, is going up, right? So again, consistent with our hypothesis that the random practice, this was not observed in the block practice, is leading to greater search of the space, both within at the joint level and at the task level. Okay. So the main conclusions were random practice led to increased search behavior at both task and joint levels, right? So both in finding effective information, the way I'd put it is both in finding an effective information movement control law and in finding finding a way to produce that law through different redundant ways, right? Further analysis of that the coordination was higher with random practice. This was encouraged more with random practice. Um, they they conclude that there was an overall effect on task affordance, although I think there was a little bit of evidence, but the overall maybe it wasn't significant. Um, but the in terms of the overall performance, but they are getting at the amount and the structure of the variability it's causing of things. So again, I think this is a really good study. Again, it's going beyond just the typical show the overall performance effect. It's diving in why. Why does variability of practice lead to better performance, right? Because it encourages more search and more effective search. You're seeing here encourages repetition without repetition, increasing good ratio of good to bad variability. So I think it's this understanding why variability is effective, right? And this is something I also in the early in the year I talked a little bit about how variability effect a practice affects the usefulness of different information sources. Here we're focusing more on the movement side of things, but variability practice, the reason I call it the lowest hanging fruit, it has multiple benefits, and here's yet another one. So overall, I think this is a really good study, and I want to encourage you to read the paper if you're interested. So thanks for joining me. Cheers for now, and keep them coupled.